So continuing with the error, if we're looking at a Taylor series in general, all right, keep in mind what the Taylor series is actually doing. We create the Taylor series by working off of some original function, and we're finding all the derivatives of that original function, and then we're writing a polynomial based on the values of all the derivatives at some particular point where we're saying is the center of our series. Right? So you can see this from the first bullet point. The Taylor series is going to be exact as the function. They're going to be one and the same on the interval of convergence. Now, the interval of convergence might be a set value of terms. It might only be one number. It might be all real numbers. But whatever that interval of convergence happens to be, the series and the original function that we're working with are going to be one and the same. They're going to have the same values. Okay. Now, what's the problem with that? Well, if we're trying to write a series, we know that a series has an infinite number of terms. We just don't have the time to go through all of those terms. Right? So what do we do as mathematicians? We tend to stop after a certain number of terms in this Taylor series. Once we stop looking at all the terms and we only look at a set number of terms, we no longer have a Taylor series. We've got ourselves a Taylor polynomial. Right? So there are a finite number of terms. And because there's a finite number of terms and not all the terms, we no longer have an exact answer. We're only going to be able to come up with an approximation when we're dealing with, okay, here's the Taylor polynomial. It is working together with the function on our interval of convergence. But because it's a polynomial, we don't have all the terms. So what's the potential difference, all right? And the mathematical term for that potential difference is actually called the error bound. How far off is our approximation from the actual value of the function? Right. Well, Taylor had a theorem involving that. Right. Taylor's theorem is basically that saying that, okay, well, let's look at it this way. The function that we're dealing with, that we were given, that we found all the derivatives of, that's equal to the Taylor polynomial that we created, which is going to be n terms long. Maybe it's 5 terms long, maybe it's 55 terms long. It doesn't really matter how many terms it is, but once we stop taking terms, all right, well, all the remaining terms, that's our remainder. If we add the remaining terms to the original Taylor, then we end up having that function, right? So let's focus on the remaining parts, okay? The remaining terms, that remainder right there, okay? And when we do that, well, that remainder, all right, now we're looking at, we have in essence the absolute value if we're going to subtract the Taylor from it. So we have the absolute value of the original function and the Taylor polynomial. All right, that's what the remainder is going to be. All right, so when you see that expression, an absolute value of a difference, we're talking about what's the remainder. Okay, and the remainder is, well, we already did n terms, so we got to go to the next derivative, the n plus 1th derivative. And we see the n plus 1 factorial in the denominator and the x minus a to the n plus 1 power. The only difference is we see the c right here. What's that c? Well, that c is some value between where the series is centered and the approximation that we're interested in. So if, for example, the series was centered at x equals 1, and we're doing an approximation of the function at 1.2, then that c value needs to be somewhere between the 1 and the 1.2, right? And that can get a little confusing because how do we find that next derivative and how do we find that value? But we're going to kind of modify that into what's known as the Lagrange error, and that's going to be in the next video.